How are you doing today? I'm a computer science professor. I love coding and I love teaching. If there is one place where I can bring both of these together, is in my classes on data structures for students here at Christ University. This video session is relevant to all those who want to get an insight into programs' efficiency without drowning in the sea. C is a programming language, a language which is a software programmer understands. She is able to instruct the computer using code as to what action has to be undertaken. The computer does not understand C, and it will require another software called a compiler, which converts the programmer's readable format to a machine readable form. Thus, a C program, which in reality is just a text file, gets converted into an executable. Computer has random access memory, RAM, and a hard disk. We store files on the hard disk, but if we want to do some processing, we need RAM. Both can store information, but the difference is that though RAM is very fast, it is volatile in nature. When you switch off the computer, everything on the RAM is lost. RAM's access is very fast, but with speed, cost goes up. So normally the ratio of the sizes is heavily skewed towards the hard disk. I have a laptop purchased 2 years back which has 4 GB of RAM and 320 GB of hard disk. This slide shows relative sizing of both. A simple analogy is if we can consider the memory power of our brain as RAM and a notebook or textbook as hard disk. Adding 3 numbers in the mind is definitely more easier than opening the book, locating the page where we wrote the 3 numbers, reading the 3 numbers, calculating it in the brain, and then answering. Computer programs is converted into an executable. The executable is loaded on the RAM and instructions are executed line by line. This in short is called as running the program. It is very important that we use space in RAM optimally. In my school days, computers used to have some kilobytes of RAM, but nowadays laptops have gigabytes of it. Do we need to bother about efficiency? Well, sadly yes, because expectations from a computer has also gone up exponentially. We have video games which find 4 GB of RAM insufficient. We have data warehouses which find terabytes of hard disk space inadequate. All your music files and video files are stored in the hard disk. But when the same is played in the Windows media player, chunks or blocks of these files are brought from hard disk into RAM to facilitate smooth playing of these files on your computer. In programming parley, an array is a contiguous block of memory on RAM which can be accessed by an index. For example, ARR is an array which can contain 10 integer numbers. If I say ARR 7, I can access the value of 7th position without having to traverse the first 6 numbers. The reason this simple strategy works is because the numbers are stored in the array together. If we know the starting address, we can predict the location of array 7. Address of ARR 7 is the address of the starting point plus 7 minus 1 into 2, 2 because each integer value takes 2 bytes of space on a computer. Let us see how we can use an array. If I wanted to print 10 numbers stored in an array, the logic would be something like this. Go through the array and print each number in the array. But then when should we stop? So we modify the statement by saying loop through the array till it reaches the end, each time printing the contents at that position. But what if the array is partially full as shown here? Well, then the trick is to stop till we reach the length of the array, in this case 6. In C programming language, the code looks like this. For basically loops the contents with the curly braces till the condition variable I is less than the length is satisfied. You will notice I plus plus, which means the index which starts at 0 is incremented by 1 every time we loop through the array. The efficiency of displaying the contents of the array, as you can see, is proportional to the length of the array. If the array contains 1000 numbers, it will definitely take more time than for the case of 10 numbers. We say this as the efficiency of this code is in the order of n, or symbolically big O n. If true, display on screen found, else keep searching. If you go through the array and do not find it, then display not found on the screen. The C equivalent is written on the slide. Error: in case element is found, the output would display both found and not found. We need to do a small change. When we find the number, we should exit the code using the return statement. As shown in the example, once found is displayed, computer will not continue any further. What is the efficiency of searching the number? Well, there are 3 cases: best case, worst case, and average case. Can you pause the video for a moment and give it a thought as to what are these 3 cases? When would it be easiest to locate a number? When would it take maximum time? I am sure you would have guessed it. The best case is when the number is in the first position, say 23. Worst is when the number is not in the array, or when it is the very last number in the array. In this example, 54. We would say the best case is 1 and the worst case is order of n. Average case is approximately n by 2. For those with computer science and mathematics background, I would like to tell you n by 2 is not entirely correct for the average case. What would the average case really be? If the array contained numbers in ascending orders, would our task have been easier? In this example given, you can clearly see that if I am looking for 50, I do not need to go all the way to the end to find out that the number is not there. I can exit as soon as I reach 53, because there is no chance of 50 being after 53. Best case is still the same, but the average case will be much better. Even if the number is not in the array, we can exit much earlier. Have you played the game 20 questions, where you simply find out the solution by simply asking many true-false questions? If I want to find out when is your birthday by asking you true and false question, how many steps would it take to find your birthday and month? If I was doing linear search, I would start at Jan 1st, no, Jan 2nd, no, and keep asking till I find out when is your birthday. In the worst case, if your birthday is on 31st December, it would take me 365 questions. Can you think of a faster way to get the answer with minimum questions? Luckily, there is a much faster method called binary search. Question would be, is your birthday before June? Yes. Then is your birthday before March? No. Is it before 15th April? Yes. Is it before 22nd March? No. You can see what is happening here. I am splitting the search area in two halves and hence eliminate half possible answers with every question. In this case, as shown in the slide, you can see it took just 8 steps to identify the birthday. If there are 100 numbers in an array and we were using binary search, then we will jump to the middle, that is the position 50, and check if the number I am searching is bigger than the current number. Before ARR 50, yes, we eliminate 50 numbers. Before ARR 25, no, we eliminate 25 numbers. Before ARR 37, yes, we eliminate 13 numbers. We eliminate 6 numbers, we eliminate 3 numbers, we eliminate 2 numbers, and finally we eliminate 1 number. This efficiency works out to be log n base 2. Log n is the number of steps to bring a number down to 1 by dividing the same number by 2. So for 10, log n base 2 is 10, 5, 2, 1. So that is 4 steps. For log 100, we will go 100, 50, 25, 12, 6, 3, 1, 7 steps. Can you take a guess as to how much would be log million? Or in other words, if there are a million numbers, in how many steps would we be able to find a number we are searching for? When I ask this question in class, I normally get wrong answers. Some assume it would be 20,000 or 10,000. In rare cases, 1,000. Well, the answer is around 20 steps. When we keep dividing by 2, numbers become small very rapidly. For the same matter, when we start with 1 and multiply by 2, let's see the steps to reach a million. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. If we think 1024 as 1k, then to reach a million just takes 10 more steps. 1k, 2k, 4k, and like that 512k, 1024k, which is 1 million. I am sure you see the beauty of binary search. I can search for a number in a million numbers in just 20 steps. This is the average case. Linear search would take on average 50,000 steps. Compare 50k to 20 steps. Please note there is a catch here. The array should be in ascending order and we cannot do binary search in case the array is randomly populated. Log n will appear many times. Sorting an array into ascending order takes n square. If you use a strategy to sort the array called selection sort. But if we use a method called quick sort, we can do it in n log n steps. Selection sort will take 1 million steps to sort 1000 numbers. Quick sort created by CAR Hore will take 10,000 steps only. Compare 10k with 1 million. Definitely, quick sort is much faster. Please attempt the quiz provided in the learning management system to assess how much you are able to grasp from this video session. So until next time, happy learning.